Okay. All right. Yes. Thank you, Raja. Thank you, Kaixiang. Thank you, everyone.
Jamika, before I run off, I'll just say a quick word and say hello to Rob, Rohit, Aparajito, Preksha, and Alisa, your old hands at Shadow the Scientist. So welcome back. Yet again, we have a night without, where we can't open the telescope because of bad weather. But you're in good hands with Jamika and Kaixiang. So I'm going to sign off, leave them to it. And again, I will see you on our next STS night, hopefully, which will be in March. And we'll announce that on our website. All right. Thank you.
Have a good time. Enjoy the rain.
Thank you.
Yes, enjoy the rain and birthdays.
Jamika, I'm making you host.
Yes.
And recording is.
Yes, recording is. It has already started.
Thank you. Okay, I'm assigning you as host when I sign off. Okay. Take care.
Okay. Aloha, Raja.
Aloha.
Okay. All right, Kaixiang, take it away.
Okay, so maybe I can start. Hi everyone. First, let me introduce myself. I'm Kaixiang Wang, a 5-year graduate student from Peking University and the Kavli Institute for Astronomy and Astrophysics. So during these 3 nights, we were supposed to be observe some of the very interesting objects, which is called the ultra compact dwarf galaxies. And as you know, that actually, as you can see, the weather is really terrible. So we actually don't even get any data from this observing run. And yeah, we travel far from, for me, example, I came from recent visiting CFA, so I travel from Cambridge, Boston, and took like 11 hours flight to the island, but we just get nothing on observing. So sometimes it looks really discouraging, right? But it's some of the experience that astronomer minds. If you have a long career, like with a long enough career, maybe everything can happen. So you just need to accept everything that you cannot control weather, especially weather is, relatively speak, that the weather during the winter months on Maunakea is the worst. The winter months like roughly represent from December to February, maybe to March. During this time that the summit can be really cold, and there's usually will be snow. And there are 2 things that might influence the observing. One thing is mainly because apparently that if there's like heavy snow or rain or it's foggy on the summit, then or with high humidity, so the dorm will not open. There's also another possibility that even if it's not rain or snow or the foggy, if the weather is calm, but if there being like recent snowfall and there being some like many ice accumulation on the dorm, or the road have ice which prevent people to come to the summit, there'll be certain problem that such ice condition can be maybe harmful to the observatory, the telescope, or to like the crews who travel back from the mid-mountain and to the summit, which certainly will also influence the operation of the telescope. And recently, we're unlucky that, well, it's probably the worst period among the year, that in about 10 days, I think the Maunakea or all the telescopes during the past 10 days, they only opened for observing for less than 3 nights. So it's really bad. And in the following next week, maybe there's still lots of snow and lots of precipitation going on. So actually, how many nights during the next week can be observed? We don't know actually. Yeah, so Jamaica's send a link to the Maunakea weather. Maybe you can take a look at them. Can you see screen? Actually, this is the weather forecast for from the Maunakea Weather Center, and it is a like graphical chart that you can see what will happen in the next few days. That it's really unusual. If you see the first row, which shows the red column, shows the possibility of the precipitation, and the blue column shows another possibility for the foggy weather. So you can see almost in 1 week, in the next 5 days in 1 week, the possibility of the precipitation is pretty high, and no need to say during the today and tomorrow, actually, there's no possibility to get observed. And you can also see on the second row that the cloud coverage, which shows that this actually almost 100% of the cloud coverage. And also the cloud height is never below the summit altitude, because sometimes you certainly will be like raining at the sea level, that the towns on the Big Island, they have raining, but the summit can actually above the clouds, so it could be really clear during the night and would be good for observing. But obviously this is not the case. The temperature also very low, because you can see the temperatures among like -1, and which is the frozen condition, which is really bad because ice will accumulate a lot. And the water vapor is also high. It's everything you can imagine that is, well, it's really bad. There's no way we can observe or get any data. So maybe let me introduce a bit let me introduce a bit about the project of our the observation, that we are pretty interested in observing a certain strain population in the galaxy population, which is called the ultra compact dwarf galaxies. So ultra compact dwarf galaxies, imagine their name, that they're ultra compact. So why they are ultra compact? Let me show you some of the image of them.
And while Kaixiang is pulling up those images, I just wanted to say, wow, wow, wow. In South Africa, you're saying lots of rain there. Is this Annalise?
Yes, Tamika, indeed. We've been having this La Nina effect right now. Some areas have been designated as disaster areas due to the downpours that we've been having. Quite a lot of rain, sinkholes that are forming in Centurion, which is about 40 kilometers south of Pretoria. Dams are overflowing, rivers are gushing. So yes, lots of rain right now. I know that later in the year the El Nino is going to become a bit stronger, so we will again turn to becoming more drought stricken. So we are so appreciating of the rain, but many days right now we've had literally it's a downpour. Low-lying breaches are overflowing with rivers and so on, so you have to take all sorts of routes through the city in order to get to your home. And sometimes you get the occasional overspill of your sewer systems also because of the amount of water that's currently all over the place. But as I say, we're glad, we're grateful. I've planted grass this afternoon, and I hope the rain that is about to fall will surely make them grow a lot faster than otherwise. Thank you.
Thank you for sharing, and we'll certainly keep you all in our thoughts, that you will be safe. Thank you for joining us during all of that, Annalise. Thank you so much for sharing. Okay, Kaixiang. Oh my gosh, this is beautiful. Ultra compact dwarf galaxies.
Yeah, so we were pretty interested in the origin of ultra compact dwarf galaxies. So why they are so compact? If you look at the image, on the right-hand side, that obviously there are hundreds of dwarf galaxies in like the nearby galaxy cluster, for example, the Virgo cluster and the Maunakea cluster. There's many more in the more massive Coma cluster. So the dwarf galaxies, usually their half-life radius, their size will not smaller than like 1,000 parsec, 1 kpc. And for ultra compact dwarf galaxies, they have the similar stellar mass compared to those low mass dwarf galaxies, which is between 10 to the 6 to 10 to the 8 solar mass, but they are much, much smaller. So their typical size is only about 10 to 100 parsec, which is like over 1 to 2 order of magnitude smaller than normal dwarf galaxies. Yeah, so if you look at the image, these two images of the zooming image of the dwarf galaxy and ultra compact dwarf galaxies, they're actually on the same scale. So you can directly compare about their sizes. So if you just look at the UCD, the ultra compact dwarf galaxy image, you just feel like they actually looks very similar to maybe some of the background galaxies or thousands of global clusters in the cluster, in the galaxy cluster near 87. So basically, they just look very similar. So this is why actually people have been overlooked them for a long time. People just think, oh, this near point source, it seems we cannot really resolve them. So maybe they just global clusters, or maybe they just background galaxies, or some of, especially for some of the really compact ones, they may just look like to the point source, maybe the foreground stars. But well, in about 20 years ago, people do the research in the Fornax galaxy cluster, and they realize that many of these point source-like objects are actually in the Fornax cluster because they get spectra for many of these objects. And the velocity information shows they have the radial velocity consistent with other galaxy cluster members. So which means they are in the galaxy cluster, they are not background galaxies or foreground stars. And compared to their luminosity with other normal global clusters, they are actually much brighter. And if you fit their structure, you find that the size of these ultra compact dwarf galaxy actually still much larger than normal global clusters. For example, on average, the normal size of the Milky Way global clusters are just less than like 5 parsec. But for ultra compact dwarf galaxies, many of them are actually larger than like 20 parsec or 30 parsec. So which actually they still have the large difference. And also the ultra compact dwarf galaxies are much more massive than normal global clusters. For example, a typical ultra compact dwarf galaxy is more massive than 10 to the 6 solar mass. But for typical global clusters, their size, their mass is about 10 to the 4 or 10 to the 5 solar mass. There are certain some example. For example, the brightest global cluster in our Milky Way is the Omega Centaurus in the southern sky. Maybe you can see them with your naked eyes in the south hemisphere. For example, if you are in Chile, you are in Australia, New Zealand, and also even if you are in northern hemisphere, if you're close to the equator, like if you are in Hawaii, you can also see the Omega Centaurus. The Omega Centaurus have the stellar mass about 10 to the 6 solar mass, which is just around the similar mass with some of the ultra compact dwarf galaxies. So people argue that maybe the Omega Centaurus is also a type of the ultra compact dwarf galaxies. It's not just a star cluster. Yeah, and there's also a huge diversity in the galaxy population that in recent years, the people have more and more interest in the ultra diffuse galaxies. Here's another comparison about the huge diversity between the ultra diffuse galaxies to the ultra compact dwarf galaxies. You can see the ultra diffuse galaxies, we call them ultra diffuse, which means they have extremely low surface brightness. And what cause they have so diffuse structures? Are they normal dwarf galaxies? How to form galaxies which are so diffuse and large but really diffuse and faint? How to form the ultra compact dwarf galaxies? So these are very interesting questions. Currently there is some of the different scenario about the formation of these ultra compact dwarf galaxies. There's one possibility that these ultra compact dwarf galaxies are just the most massive star clusters, that they may be formed by the merger of massive star clusters. For example, there's like 2 or more massive star clusters, they can merge. So after they merge, they can become a much more massive star clusters, which have the similar size and similar mass compared to the other ultra compact dwarf galaxies. So there's certain possibility that those ultra compact dwarf galaxies are just the brightest global clusters. And there's certainly another possibility that sorry, let me close this. Yeah. Let's go back. Well, sorry. The second formation scenario for the ultra compact dwarf galaxies is they do come from the dwarf galaxies. They are the remnants of dwarf galaxies. This is the situation is during the close interaction between those dwarf galaxies with massive galaxy, for example, MA87 in the Virgo cluster. The close interaction means that the dwarf galaxy will have strong tidal interaction between the dwarf galaxy itself and host galaxies. So the strong tidal those strong tidal force will disrupt the structure of the dwarf galaxy, which will strip the stars from the dwarf galaxy and make it to become less and less massive. And also it will create that some of the tidal features or tidal tails that stretch for much, much longer. For example, there's certain possibility that there's observations that we have observed those very long stellar streams that belong to, for example, the Sagittarius dwarf galaxy near our Milky Way, which shows the Sagittarius dwarf galaxy is being tidally disrupted and create extremely long tidal streams. And this is around the Milky Way halo. And usually for dwarf galaxies, they have a stellar nuclear star cluster nuclear star cluster in their center, which is a majority of the dwarf galaxies in a certain mass range. They have the nuclear star cluster. So if the galaxy itself is being totally disrupted, as you can see in the middle of the image, that there's a dwarf galaxy with a central nuclear star cluster. So if the outskirts of the galaxy is being totally disrupted, then because of the central nuclear star cluster is very dense structure, so it can resist the tidal disruption. So it will remain mostly stable during the close interaction between the dwarf galaxy and the host galaxy. So it will remain and become a remnant structure of the totally disrupted dwarf galaxies. In this way, actually, it can be really interesting that the galaxy itself, it seems that it's back to the star cluster, right? So in the beginning, there's a normal nucleated dwarf galaxy with a central star cluster in the center. And then the galaxy itself is being totally disrupted. And so the only left over is the central nuclear star cluster. And it seems this is indistinguishable to other star clusters, the remnant stellar nuclei, the nuclear star cluster. So it shows a morphological transformation from galaxies back to the star cluster. And also, you can use them to trace for example, the accretion history of the most massive galaxies. Because the most massive galaxies, their growth is by accreting lots of the low mass dwarf galaxies, and also they have major mergers, which is they have merged with other massive galaxies to become a really giant elliptical galaxies. There's certain example. For example, our Milky Way will collide with Andromeda galaxies in the future. That the two disk galaxies, the spiral galaxies, will finally become one giant elliptical galaxies, which is really interesting. So these things happen in our universe, like every day. There's lots of galaxies, they merge, their interaction. So here, the formation, if UCD are formed through the disrupted dwarf galaxies, there's another example shows how the environment, for example, near the host galaxy, the massive galaxies, will influence the evolution of those galaxy populations. How those tidal interaction can shape the morphology of those dwarf galaxies. Oh, there's another possibility that these ultra compact dwarf galaxies are just formed with very dense, very compact structure. They form in a dark matter subhalo but their size are actually much smaller than typical dwarf galaxies. Yeah, so these are the current theories about those ultra compact dwarf galaxies. I think, yeah, I can stop share these slides and I can show you some of the other materials. Is that okay?
Oh, absolutely, absolutely. And I was going to say that Aparito has a comment and question here. Says, Aparito, would you like to read your comment and question while Kaixiang is switching?
Yeah. Hey, Kaixiang. So I thought the thing that separates star clusters from the smaller dwarf galaxies is dark matter content. Am I wrong?
Yeah, right.
So, like, can we look for dark matter to, test if UCDs are in fact formed through channel 1? How would you even go about that?
Yeah, this is what we plan to do during our observing. So how to distinguish how can we tell that a star cluster like UCDs come from the ancient dwarf galaxy, which is being tidally disrupted? There's some evidence which can show you that they may be past dwarf galaxies. For example, there's two main criteria to distinguish the galaxies with star cluster, that the galaxy formed in a dark matter subhalo, right? There's dark matter content inside of them. Another criteria would be like, because the galaxy is a complex system, so it's experienced a very extended star formation history. There's multiple star formation events and complex stellar populations. But for star clusters, we assume that most of the global clusters, their stars just form at once. So there are two things that we can really distinguish them. Can we find dark matters in those ultra compact dwarf galaxies? Another thing is about their stellar population. Do they have very complex stellar population or extended star formation history? There's third evidence come from that do these ultra compact dwarf galaxies have supermassive black holes? And so these are the very interesting things, and we want to look at. So our project is that we want to measure some of the massive ultra compact dwarf galaxies about the motion of their stars, about their velocity dispersion. So imagine if ultra compact dwarf galaxy, it have a black hole, supermassive black hole inside of them, or it have like dark matter content of them. The motion of stars will be, or the velocity of dispersion of all the separate stars will be higher than it's just a global cluster without dark matter, without, for example, the central supermassive black hole. So we can infer this from their spectra, from their velocity dispersion. So we want to see, is these ultra compact dwarf galaxies have really high, unexpected high velocity dispersion, which provides some of the evidence to see for this population, how many of them have very higher velocity dispersion and elevated like mass to light ratio, which is the stellar mass, not stellar mass, the dynamical mass to the stellar luminosity ratio, which can indicate maybe there's more mass like inside of the ultra compact dwarf galaxies. Can be maybe dark matter, maybe if you look very detailed with very high resolution, there's certain previous study to find supermassive black holes in the UCDs. So they use like adaptive optics that can resolve the central velocity dispersion. There's a peak in the central velocity dispersion profile, so which indicates that there's a massive objects in the center, which can be said that this is actually a supermassive black hole. So these are the very interesting things that we want to look at. Well, unfortunately, we can't get data from these 3 nights, but we have half of our observing time during this semester. Hope we'll get more evidence about their origin. Yeah. And these things actually can be expensive, that because you want to get spectra, you want to get them one by one. Actually, there are hundreds of ultra compact dwarf galaxies for example, in Virgo. But it's really hard that you do them one by one and get their high resolution spectra, which we can get their velocity dispersion, or even, for example, their black holes. We have another proposal to use JWST to search for the supermassive black holes in some of the ultra compact dwarf galaxies and compact elliptical center, which is to see what their black holes can we find black holes in these like tiny compact stellar systems? Yeah, so these are in observation, they can be more expensive, but we can also infer whether these dwarf galaxies come from these ultra compact dwarf galaxies come from dwarf galaxies. It's just from their morphology. I can share another material to you.
So while you're getting ready to share that, thank you, Aparajito, for the comments and questions. I just wanted to get a bit of clarification. So are you all still working to clarify whether there are black holes in these UCDs or not? Or is there an overall a general consensus that it's possible, but follow-up observations are required to really get a more definitive, firm grip on the answer?
We expect that actually lots of the high mass ultra compact dwarf galaxies, they should have like black holes, maybe not so supermassive, but can be the like intermediate mass black holes, which is 10 to the maybe 10 to the 4, 10 to the 5 solar mass. Black holes inside of them. But we expect that most of their dark matters have been stripped, because during the tidal stripping, not only the stars can be stripped, actually the first thing to be stripped is the dark matter. Because after the dark matter can be stripped, dark matter provides those gravities, so it can constrain like the stellar motion. So if most of the stars is being stripped, then which means most of the dark matter is also being stripped. So it would be hard to really find like if there are like certain UCDs that form like it's really just inside a subhalo with lots of dark matter inside them, but we can still find maybe some signature from those of the information, for example, their velocity dispersion information and their morphology. And so here I can show you that I show you some of the UCDs in the next generation Virgo cluster survey. You can notice that the left-hand side is their color image. We use their color ComSci image, which shows they are really compact. And the middle is their contour with different surface brightness level. And the right-hand side one is of their radial surface brightness profile. So actually, even if in the ultra compact dwarf galaxy population, you will notice some of them are different. For example, the first one, the NGVS UCD 112, you will notice this is more diffuse, right? This is actually more diffuse than the UCD 240. In the upper ones, actually, if you look at their profile, you can notice compared to the gray dashed line, which is a single point spread function. The first one, the UCD 112, actually shows the diffuse stellar envelopes that it can be fit by a two-component profile rather than just a one component compared to the UCD 240. There's some better example. For example, you see that the UCD 374, this one is much more obvious that it's really extended. This is more like a dwarf galaxy, but actually its size is pretty small. That the half-light radius, the size is only like 30 to 40 parsec, which is still an order of magnitude smaller than most of the dwarf galaxies. But you look at its structure, that you will clearly to clarify that this one, that it can be resolved with a nucleus with a diffuse stellar envelopes. And there's also another possibility. There's some other examples about, for example, the UCC 766. Oh, this one is really that diffuse. This such two component profile with other of the one component profile. For example, UCD 507. This one, you won't notice there's any excess light in the outer region, that this UCD do not have stellar envelopes. So these stellar envelopes can be some of the independent evidence to show that these UCDs with stellar envelopes, they are from the disrupted dwarf galaxies. Because for the disrupted dwarf galaxies, they actually can be much diffuse in the past, that they have much brighter and much larger the stellar envelopes. For example, this one, you will notice there's a nucleus and very extended stellar envelopes. But for this one, the nucleus is much prominent compared to the outer components, those stellar main body. And for this one, you can see, do you think this can be still decomposed as like two components? Maybe you will notice that there's some light still in the outskirts that cannot be well fitted by these single components. So these provide some of the independent evidence that those ultra-compact dwarf galaxies, some of these ultra-compact dwarf galaxies, if they have diffuse stellar envelopes, that they come from former disrupted dwarf galaxies.
This has been amazing explanations. It's really detailed, and I certainly hope I am speaking for everyone that certainly appreciate the time and effort you put into not only creating this awesome PDF, by the way, that Kaixiang did, but for me, it's really helpful as the visualization allows me to really follow much better what you're saying and your explanation. In our last few minutes, Kaixiang, I'd like to turn your attention to the chat. Parajito has another question and some comments. Parajito, would you like to share that with Kaixiang?
Yeah, sure. Hi, so you were talking about some intermediate black holes, like possibly. So can we really narrow down the mass of the black holes enough to tell, to be able to tell whether or not they are intermediate black holes, because intermediate mass black holes, because they are really interesting, and there's a lot of mystery surrounding how they're formed. So it would be interesting to find a whole new population of these intermediate mass black holes in these UCDs.
Yeah, so we can roughly estimate about the black hole mass in in those UCDs, because usually there's like the black hole mass and bulge mass relation, the black hole mass to the stellar mass relation. Here, because those UCDs, we think that they have been like tidally disrupted. So usually the black holes will seem to be overmassive to its total stellar mass. For example, there's a previous discoveries about a black hole in the massive UCD M60 UCD1, that the black hole itself actually constitute about it's about 15% of its stellar mass. So that's one thing we can estimate, that we estimate there can be overmassive black holes. For example, if the UCD itself is a 10 to the 6 solar mass, which means the black hole mass will mostly like located between around a few to the 10 to 4 solar mass to the 10 to 5 solar mass. So which is the range on the upper near the upper limit of the intermediate mass black holes, but we but we think there could be some of these objects inside of them. And also there's another possibility that because there could be some of the fainter dwarf galaxies, and they stripped and their nucleus is actually fainter. So they're not necessarily that the stripped nuclear star cluster can be fall into the UCD population. They can be less massive, and we found them to be just in the global clusters. So there are certain, we think that certain be a fraction of the global cluster, then they can be stripped nuclei that, for example, there are certain, like in our Milky Way, the M54, the global cluster is the center, the nucleus of the Sagittarius dwarf galaxies, and it's less massive than our typical UCD selection. So in these, for example, if there's a 10 to the 5 solar mass UCDs, or we can call them like stripped nuclear star clusters, and there certainly will be 10 to the 4 solar mass black holes inside of them. And recently there's some study to claim that they have discovered like the intermediate mass black holes in like M31 luminous global clusters center. So this could be interesting. That that's one thing we will be trying to do, that to searching for intermediate mass black holes or supermass black holes in those ultra compact dwarf galaxies and global clusters. Yeah. Can I do I ask answer your question?
Yeah.
Fantastic. I want to be respectful of Kaixiang's time. It is just a little bit after 5 a.m. There in Hawaii. I wanted to ask for anyone else who is with us today, are there any last questions or comments for Kaixiang? Okay, and certainly if you have any thoughts later on that you have thoughts of questions that you'd like to share with Kaixiang and the rest of the team, please feel free to email us. You have the email address from the promos that I sent out. Please feel free to send your questions there, and I'll be sure that they make their way to Kaixiang and Raja and the rest of the team. I'd also like to just send a shout out to Anand. Anand is he's my colleague here at UC Santa Cruz. He's part of the CREST team, which is the Creating Equity in STEAM, under which Shadow the Scientist falls. Yes, Anand, thank you so much for being up early there and joining us. We really appreciate the support. And I want to thank you all for joining us. And I very much look forward to seeing you in our next session. We'll be posting those. We have some already posted for March. We do have 4 more coming up as well that I will get posted here in the next few days. I'd like to thank you all again so very much. Kaixiang, you are a warrior. And I do hope that your next nights on Keck are you are not weathered out.
Yeah, I really hope. Yeah, I think bad luck will just go. We'll finish.
Yes. Well, I hope that you get some rest there in the beautiful town of Waimea, there in the where you are at the Keck headquarters. And I also wish you all a great rest of the day. And Annalise, again, we will certainly keep you in our thoughts for your safety and all of you in your area there in South Africa. Rob, Aparahito, Adriana, and Preksha, I apologize if I mispronounced your names, but I do want to say thank you all for being here. Any last words, Kaixiang, to you?
Yeah, thanks everyone for joining today. And yeah, I'm very happy to share of this interesting objects to you. Sorry, we don't have a chance to show you like those observation. There's certainly no chance to do this, but I'm still very happy to show you about what we intend to do, about our like purpose, how to like shed the light on these the mystery objects. And I hope I can find more answers in the future and show you more of the cool results.
We definitely look forward to that for sure, Kaixiang. All right, well, I wish everyone a wonderful Saturday, and we'll see you at our next open session for Shadow the Scientist. Mahalo nui and aloha.
Mahalo, yeah.